Welcome, my dear warriors. Welcome back to the Vedantu JEE English channel. And we are on to the chapter of ray optics, the class 12 syllabus, the lecture number 3. In the first lecture, we did plane mirrors. Second lecture, we did curved mirrors. Today, we are going to do plane surface refraction. In the next class, we'll do curved surface refraction and lenses. Okay, so that's the flow of the topics. We are keeping it very systematic right from the scratch, from basics to proper JEE level. So this is your Captain Shreyas. I hope you guys are doing great and I hope I'm audible and visible to all of you. Quickly let me know in the chat box, everyone. Yep, nice to see all of you. Hi. Manoj, good evening. Good evening, everyone. Yes, this is your Captain Shreyas, my brief introduction slide. If you are new to the channel, subscribe and also like the video because that is what motivates me and the entire team over here to produce more such quality content just for you. Okay, so let's begin. It's a big chapter, heavy weightage. So let's get straight into refraction, guys. And if you have not yet registered for MVSET, please do that right away, right now, because this Saturday, Sunday, we had an amazing MVSAT event across the country. So many centers, so many students, thousands and thousands of students already giving the exam, and the results will come out soon. The last two dates are 11th and 12th October. Nearest Vedantu Learning Center, you are not only getting All India rank, but a lot of prizes, scholarship, gifts, getting to meet teachers, getting to know more about the exam, the competition, the strategies. All right. So be there. The last two dates are 11th and 12th October. Cool. So let's begin. Yeah. Welcome aboard. Hi Rohit. Hi Valesh. Welcome. Hi Hari. Hi Praga. Good evening. Good evening. Hi Gayatri. Welcome. Welcome. Manoj, you already completed the MVSAT. Rahul, this is not one shot. This is detailed classes separate. Valesh, welcome. Welcome. Thank you so much. Sampreet. Yes. Pahul sir is already there in your Sigma batch. Okay. So let's start with the concept of refraction. Refraction means whenever there is a medium change and the light is changing that medium, then you will see the speed of the light will change and the direction will also change. So in case of refraction, basically the path of the light, the path of the particular light, the path of the light changes direction, changes direction, changes direction. Number one thing, changes the direction. Number one thing. Number two, number two, number two, the speed of the light will change. The speed of light changes. The speed of light changes. That is very, very important. Now, whenever the speed of light reduces in a medium, then that medium is said to be denser relatively. Now, whenever you hear these words rare and dense, don't confuse it with kg per meter cube mass density. This is completely different density. It is just a qualitative measure. There is no particular unit or formula for it. It's just an understanding term qualitatively, no quantification of that. So when I say a medium is dense, meaning the speed of light is going to reduce in that medium. It's a relative concept. When I say a medium is relatively rare, then it means the speed of light will increase in that particular medium as compared to the previous medium. So if you take the example of air and glass or air and water, water or glass is denser with respect to air. Meaning when light goes from air to glass or water, the speed will reduce. But in the reverse scenario, if there is a torch inside glass or water, the light when it goes from glass inside the air, then the speed will increase up. So that is why air is said to be rarer medium. Is this concept of density clear? Okay. So I'm also mentioning that optical density density optical density is not equal to the mass density. Keep that in mind. In fact, this optical density is just a relative concept, is just a relative concept, qualitative concept. So whenever I say the medium is dense, the speed will reduce. The speed will reduce. And when I say the medium is rare, then the speed of light will be more in that particular medium. Not just that, look at how the light ray bends. When light goes from rare to dense, it will bend towards the normal which is drawn. This is that normal. As you can see, this is the normal which is drawn. When light is going from air to glass, rare to dense, it will bend towards the normal. But when it goes from dense to rare, like imagine the rays were drawn in the exact opposite direction, it will bend away from the normal. So that is another simple characteristic by which you can understand whether a medium is rare or dense. So say for example, I show there is an interface which separates two different medium, and I tell you this is the normal drawn, and I tell you light is coming like this and it is going like that. From this diagram, immediately you can see here the angle is only this much with the respect to the normal. Here the angle is too much. So clearly from this it is very evident it is bending away from the normal. So definitely this will be rare, and this is towards the normal. Definitely this will be dense. Here the speed will be less, here the speed will be more. Is that clear? How to identify whether something is rare, dense, bending away, bending towards, speed comparisons, etc. regarding refraction. Yeah. Yes. Perfect. I hope this is absolutely clear. Manoj, don't spam, my dear. Yeah. I will make a separate video on that username. Yeah. ITX Batman, I think you should get in touch with the Vedantu support team, but usually it is not possible to change the mobile numbers. But even if there is a slighted chance, you just email to vcare@vedantu.com. Okay. Now, having said that, let us also talk about something called as the refractive index concept. Refractive index concept, and then we will go to the laws of refraction. Sorry. So this is vacuum, this is some medium. The speed is v, here the speed is c. This c is nothing but speed of light in vacuum, which we already know is nothing but 3 into 10 to the power 8 meters per second. That's huge speed. That is a standard value of c, which is the speed of light. You have already seen that in modern physics maybe, or even in chemistry and so many other places. V is the speed of light in that particular medium. Refractive index of a medium, okay, I'll write it down over here. Refractive index of a medium, refractive index of a medium, mu of that particular medium is nothing but speed of light divided by speed of light in that medium. That's it. C by V. Speed of light in vacuum upon speed of light in that particular medium. That's it. That's how refractive index is defined. Whenever light enters some medium, the speed reduces. So V is generally lesser than C. So this ratio becomes more than 1. So the refractive indices of all the medium are more than 1. Okay, so keep this in mind. So the refractive indices of all the mediums are more than 1 because the speed will reduce. So V will be less than C. Numerator is more, denominator is small. So the ratio naturally will be more than the number 1. Is this absolutely clear, my dear students? Yeah. So vacuum and air is same. Not exactly. It's almost same, but not same. Like when light goes from vacuum to air, the light bends so small and the speed changes so small that refractive index of air, roughly we take it, refractive index of air, we almost take it as a refractive index of vacuum, which is nothing but 1. For vacuum, it is perfect 1 because imagine this is vacuum, this is also vacuum. Speed will not change. C will remain C. So denominator will still be C. Numerator and denominator will cancel and refractive index of vacuum will become 1. So Refractive index for vacuum is exactly 1. For air, it is like 1.000 in the fourth decimal, some small number will come. So because it is like 1.00027, something like that, we almost treat it like vacuum or like 1 only. Is that clear? Okay. I think so, ITX Batman, you should be able to do it. Just get in touch with VCare. If not, just message me on Telegram, Captain Shreyas, okay, with your screenshot, everything. I'll try to work it out for you, okay. Next important thing, let me show you some values of refractive indices of some common materials. Like this is for air, refractive index of glass. So when light enters into glass medium, the refractive index is basically 1.5, or you can just say it is 3 by 2, one and the same thing. Similarly, refractive index of water is 1.33, or you can also say it is 4 by 3, because 4 by 3 is also 1.33 recurring, but okay, till 2-3 decimals you can take. Okay, refractive index of diamond, etc., is very, very high. So refractive index of diamond is around 2.4 to 2.5 around that particular range. Okay, so these are the refractive indices of common materials which you should be well aware of. Not that they will exactly ask you, but better to know this. Okay, now whatever refractive index we have spoken about is the refractive index of the medium, also called as the absolute refractive index. But then there is this another term which is called as relative refractive index. So relative refractive index. So in relative refractive index, what's the difference? I'll tell you. This is no longer vacuum. This is also some kind of medium. This is some kind of medium 1. This is medium 2. This is speed of light in that particular medium. This is speed of light in this particular medium. This is C1. This is C2. Then the relative refractive index. How do we write it? Light is going from medium 1 to 2. So light is going from 1 to 2. So whatever direction it is going, first put that medium and then where it is going to. Start and end like a vector, tail, arrow, like that. Okay, 1 to 2. This 1 mu 2 is nothing but C1, whatever came first, divided by whatever came second, C1 by C2. This is nothing but C1 divided by C2. Very, very simple, very, very easy. Okay, we can play with this a little bit. Speed of light in the first medium, I can use this kind of formula, and I can say that I know one thing, that refractive index of the first medium would have been speed of light in vacuum upon speed of light in that medium. Similarly, the second refractive index would have been speed of light in vacuum upon speed of light in that particular medium. So from this, can you not see C1 is nothing but C divided by C1 is nothing but C divided by mu1, and from here we can see C2 is nothing but C divided by mu2. So substituting both of them over here, we will get C1 as C by mu1 and C2 as C divided by mu2. So what will happen next? C will cancel, 1 by mu1, 1 by mu2. So this will become mu2 divided by mu1. Yeah, can you see that? This will become nothing but, if you want, I'll just show it like this, 1 by mu1 divided by 1 by mu2, which is the same as saying mu2 divided by mu1. So that is 1 mu2 by mu1, which is also nothing but C1 by C2. Speed wise, it is in the same order, C1 first and 2 second. But for a refractive index, it is 2 first, then 1 next. That is slightly reverse. That is something which you should keep in mind. Also notice that had I replaced or exchanged the numbers and put it as 2 mu 1, it would mean light is going from the second medium into the first medium. Then this would have been just mu 1 by mu 2. This would have been just mu 1 by mu 2. This clearly tells me this is just a reciprocal of the first ratio. So therefore, can I not extend this as 1 divided by mu, but here I will put 2 and 1. So if I reverse the direction of the light, then the relative refractive index is a reciprocal. If I reverse the direction of light, then what did I say? The relative refractive index is just a simple reciprocal. That's all. Okay, great. Yes, you can say that refractive index is inversely proportional. Yes. All right, perfecto. Shall we go ahead then? I think it's a good time that we block this particular relationship on relative refractive index. Can we find some of the common relative refractive indices with some examples? Maybe yes. Say for example, I want to find the refractive index of glass with respect to water. So see guys, whenever such a thing comes, light is going from water to glass. So whatever comes first will go in the denominator and whatever comes later on goes in the numerator. So mu g divided by mu w. Is that making sense? 1 mu 2 was mu 2 by mu 1. That is what I showed you over here. 1 mu 2 is mu 2 by mu 1. So whatever comes later on goes in the numerator. Whatever comes first goes in the denominator. Refractive index of glass, I already know. It is nothing but 3 by 2. And for water, it is 4 by 3. So 3 goes on the top. So 3 multiplied by 3. And 2 comes below. 4 into 2. So this will be nothing but 9 by 8. This is nothing but 9 by 8. Very simple. Everyone clear? Straightforward? Okay. Another example. Let's say refractive index of some material, let's say, I don't know, something like L with respect to M is equal to, let's say, 1.8, chuma some random value. Then what is the refractive index of L with respect to M? This answer will be just reciprocal because you can see the path of light has reversed. So this will be the reciprocal of L mu M. So which is 1 by 1.8. 1.8 means it will be 18 by 10. So take the simplification. This will be 5 and this will be 9. So this will be 5 by 9. That is the answer. Is that clear, everyone? This is how you can do these kind of questions on simple refractive indices. Okay. There is one more thing though regarding this particular relative refractive index or even just the normal refractive index, and that is, maybe I can put it over here. The frequency and the wavelength of light. That is also something which we should talk about. What about the frequency and the wavelength of light? Okay, so let's talk about that. One second, just happened. It's not going for some reason. Anyways, so if you talk about the first medium, the light over there will have some wavelength and some frequency. And over here, when it enters the second medium, it has some new speed, maybe some new wavelength, maybe some new frequency. But let me tell you, it is the frequency which not changes, because frequency is dependent on the source of light. So the light came from some source, maybe sun, torch, candle, whatever. So that source is the same. So the frequency, the rate at which those vibrations, oscillations, that light wave propagates is the same. So whenever you see light changing the medium, the frequency stays the same, because it only depends on the source, because the frequency only will depend on the source of light. So if you change the color of that light source, the torch color goes from red to green or yellow, so then the frequency will change. Otherwise, there is no reason for it to change. Second important thing which you should be aware of is the speed of a wave, which is also called as the wave speed, is nothing but the frequency multiplied by the wavelength. So if that is the scenario, immediately we can say that speed 1 is frequency into first wavelength, speed number 2 is frequency into the second wavelength. Naturally, if I divide both of them, C1 by C2, obviously FF cancels, you will get it as lambda 1 by lambda 2. But what is C1 by C2? C1 by C2 is 1 mu 2. So clearly, we can also say that the relative refractive index is not just the ratio of the speed C1 by C2, but also the ratio of the wavelengths as well. It's also the ratio of the wavelengths as well. Frequency will not change. This is also mu 2 by mu 1. This is also mu 2 by mu 1, which is also reverse of 2 mu 1. This is the more elaborate extended relationship, but if you don't want to be confused, let's just remove it. Okay, the other part I have mentioned it right over here in terms of refractive indices, but if you want in terms of speed and just the wavelength, this is the answer. Okay, clear till this point? Absolutely. Okay. So Hari, Haran, maybe I'll make a separate video on that for big calculations, what you should do. Yes. Yeah, even if you have another mobile, it should be the same account. Sir, how can you say wave speed as C? Is it standard term? Yes, it is a standard term. I think, Manoj, you have not yet seen modern physics or physical chemistry part. C is a standard variable for speed of light, okay, which we use. Like epsilon for permittivity, it's a number, mu for refractive index, right? So same way, C is the symbol which you use generally for speed of light. Okay, great. Now, let us look at the laws of refraction. But before that, one small thing. Let's do some few questions here and there. Second. Let's do a few questions. First question is, find the speed and wavelength of light in water whose wavelength in air is 1200 nanometer. That is the question. Whose wavelength in air is 1200 nanometer. Let's try to solve this particular question. Read it. Speed and wavelength of light in water whose wavelength in air is 1200 nanometer. So speed of light in any medium, standard formula. So refractive index in water will be speed of light in vacuum upon speed of light in water. Therefore, speed of light in water will be C divided by mu W. Speed of light is 3 into 10 to the power 8, isn't it? And refractive index of water, I just told you some time back here only. It is roughly 4 by 3 or 1.33. So let's use it. Usually that value will be given to you. So don't get scared. So this will be 4 by 3. 3 goes on the top. So this will be 9 by 4 into 10 to the power 8 meters per second. That is that is the speed of light in water. Speed of light in water. 9 by 4 is obviously less than 3. I mean, even if you calculate it, it will be nothing but 2.25 into 10 to the power 8 meters per second, which is less than vacuum, which is less than that which is there in vacuum. Makes sense. It should be less because it is a denser medium. Now, the second part asks me to find the wavelength, but I do not know the frequency, or else speed is known, wavelength is known, frequency is known, then I can find the wavelength. So instead what I can do is, I can say relative refractive index when light goes into water from vacuum is nothing but speed of light in vacuum upon speed of light in water, which is also wavelength of light in vacuum upon wavelength of light in water. This was our standard relation formula, which I just gave it to you over here. 1 mu 2 is C1 by C2, lambda 1 by lambda 2. So same way, V mu W is CV by CW, lambda V by lambda W. V for vacuum, W for water. But I don't need this. I just need to take care of these. So this number I know is 4 by 3. This one, vacuum, the wavelength is 1200. So wavelength in water is asked. So lambda water will be 1200 multiplied by 3 divided by 4. 4 goes with 12, 3 times. So this will be 300 into 3, which will be 900 nanometer. So that is the wavelength of light in water. That is the wavelength of light in water. Is that clear? Okay. Perfect. No worries, ITX Batman. Uh, Even if you are logged in into multiple devices, nobody is going to kick you out. Okay. As long as you are using that same account, it is fine. Okay. Great. Awesome. Awesome. Can we write mu12 as, yes, you can do that also, Anjana. I think some books use that particular notation, which is also fine. Where did it go? Yeah. So some books do tend to use, instead of mu and then 1 2, they use it as mu 1 2. But usually this I don't like, because then it might look like the number 12, it might be misleading. So that is the reason why I separate it out. Some books also use the symbol N and they put 1 here, 2 here, or N and then 1 2 over here. Especially NCERT uses the symbol N instead of mu. Okay, it's up to you, your choice, what symbol you want to use, what kind of notation you want to use. Ideally use it separately, because it might look little confusing when you put it on the same side. Okay, that's the only reason, Anjana, I put it separately there. Okay. Hi Aditya, good evening everyone. Awesome. So having said that, let's go to the laws of refraction. Laws of refraction. The first law is very simple. All the three things are in the same plane. The incident, the refracted. Incident is the one which falls. Refracted is the one which goes into the other medium after changing the medium. And the normal are in the same plane. That is the first law. And if I use I cap as the unit incident vector, n cap, or let's say r cap as the unit refracted vector, and n cap as the unit normal vector, then the scalar triple product, which is a dot with a cross, it's called as the scalar triple product, will always be 0. So I hat means unit vector in incident direction, r hat means unit vector in the refracted direction, n hat means unit vector in the normal direction. Whether you take it here or here doesn't matter. Anyways, the answer will be 0. Okay, this is a special vectors property in 3D, where you have three vectors, and if they lie in the same plane, then they're scalar triple product. Triple because 3 numbers, scalar because the final answer is a scalar number. Scalar triple product is a big fat 0. That is the implication of the first law of your refraction. Okay. Now, what is the other law? It is also famously called as the Snell's law. It is also called as your Snell's law. So, as per this, if I is the angle of incidence, this is the angle of incidence. Like we had angle of incidence in the reflection. This is the angle of refraction. Angle of refraction. Then, as per Snell, the first medium, whatever it is, into sine of the angle in that medium, is the second medium, whatever it is, into sine of angle which is made by the ray with the normal in that particular medium. That is simply put Snell's law. If you want, you can rearrange it. I mean, not a big deal. So sine of I divided by sine of R will be mu2 by mu1. But we know what mu2 by mu1 is. It is 1 mu2. So therefore, this is the most used and widely used form of Snell's law. Relative refractive index is sin I by sin R, or sometimes people also use this one also. It's completely up to you, whichever form you want to use. Okay, I'm just blocking one of them, but obviously the other one is equally relevant and useful. Okay, so this is Snell's law, how the angle will change when the medium changes. So one more thing over here, is this delta which you are seeing. This particular delta is called as the angle. It is called as the angle of deviation. It is called as the angle of deviation. Now this particular angular deviation does not use that formula 180 minus 2i. That was for mirror. This is a refractive surface, plane surface. So don't use 180 minus 2i. Think again, what will the angle be? First of all, if I again elaborate, this is the normal. See guys, this entire angle from here to here will be incident angle. So it is very natural that if you take these two lines, the gray dotted line and this line, this is the direction in which the ray was supposed to go, but because it got bent, this difference becomes the angle by which the light got deviated. What is the meaning of deviation? I was going somewhere, I got distracted, I went somewhere. So the amount by which you turn will become that angle by which you got deviated. So same way here, the light ray was supposed to go here, but it is now going here. So this is the deviation angle. So if these two lines are considered, it is very obvious that this particular entire angle will also be I. Out of that, this is R and this is delta. So if this much is R, it's natural that delta, which is the angle of deviation, will be I minus R, But there is a catch in this, and that catch is, suppose this is the medium, and let's say this is the normal drawn, but let's say the light is going from a dense medium to a rare medium. Dense medium to a rare medium. Then things will be different. Mind it, this will be the angle of deviation. This will be the angle of deviation. This will be I, and and this entire thing will be R, but this much alone will be I again, because if this much is I, even this one will be I, because opposite angles for two lines. So here delta will be R minus I in such a case. So if you calculate, delta will be R minus I. So sometimes it is I minus R because I is bigger. Sometimes it is R minus I because R is bigger. So to make it simple and generic, what we do is we just put a modulus symbol over there. So we just put mod to make sure that our delta value always comes out as positive, whether it is rare to dense or dense to rare. It's just the difference. So the angle of deviation is the positive difference because of modulus, positive difference of angle of incidence and the angle of refraction. That's it. Simple and easy. Yeah, perfect. Great. All right. So I think it's a good time that we start solving some questions coming up on your screen one by one. All right. So let's start solving, guys. Here it comes on refraction. Say the refractive index for glass is 1.5, and let's say the angle of incidence incidence is, let's say, 30 degrees. Question is, find angle of refraction and the angle of deviation, both. Okay, so let's try to figure this out. First of all, we have to find refracted angle, then delta, because delta needs R. So to find R, the most convenient way will be to use Snell's law. So I can immediately say that when light enters into glass, from vacuum, it will be nothing but sine of angle of incidence by sine of angle of refraction from vacuum to glass, from vacuum to glass. This value is given to be 1.5. Angle of incidence is clearly given to be 30 degrees. Angle of refraction, that is what we need to find. So therefore, sine of R will be sine of 30 divided by 1.5. Sine 30 is half. 1.5 is 3 by 2. 2 cancels, it will become 1 by 3. Therefore, angle of refraction is sine inverse of 1 by 3. Leave the answer like that, because sine inverse 1 by 3, you do not know the exact values unless you use logbook. Okay, your options will also be like that. Sine inverse 1 by 3, sine inverse 1 by 4, 1 by 5, whatever, such things. But that is not the only thing. We have to also find delta. As we know, light is entering into glass, so it is going to a denser medium. So since light is going from air to glass, which is denser, the angle of incidence will be more than angle of refraction. Therefore, deviation, I can just put I minus R. I don't have to worry about mod already. Okay, don't put R minus R, because I know R will be less in glass. So what is I? It is basically 30 degrees. What is R? That is basically, I think we got it over here, sine inverse of 1 by 3. That's it. So that is the answer. That is the angle of deviation. Is this absolutely clear, everyone? Perfecto? Okay. Let's go to the next question coming up on your screen. Here it is. Light at 45 degrees incidence deviates by 15 degrees away from the normal, from the normal and has a wavelength of 2000 angstroms. Question is, find the wavelength in the rare medium and refractive index of the dense medium with respect to the rare medium. Both the things we have to find out. Very interesting question. Let's see if you guys can figure this out. Let's understand first. Let's draw a diagram. It will be easier, or else you might make some stupid mistake. Okay, it's not intentional, but it will happen. So light is incident at 45 degree and deviates 15 degrees away from the normal. Okay, it was incident at 45 degree and it is deviating away by 15 degrees like this. So the original intended path was like this, and this was 45 degrees. This is 15 degrees. It is very obvious now that this particular medium is the denser medium and it is going away. That means this is the rarer medium. This is the rarer medium. Also, angle of incidence becomes very evident to be 45 degrees. Here, this will be the entire angle, just like this was incident angle. This will be the entire angle of refraction. That will be 45 plus 15. Agree or disagree? 45 degrees plus 15 degrees, which is 60 degrees. That is what the angle of refraction will be. I think now we can figure out what might be happening. Light is going from the dense medium to the rare medium. As you can see, the light has just gone from the dense medium to that particular rare medium. So that is why the symbols used are d mu r, first medium to the next medium. This will be sine of I divided by sine of r. So that will be sine of 45 divided by sine of r. What is r? 60 degrees. Okay. Sine 45 is 1 by root 2. Sine 60 is root 3 by 2. So 2 will go on the top. Root 3 will be here. And one more root 2 will be here. Root 2 will cancel. So it will become root of 2 by 3. That is refractive index d mu r. But the question asked is r mu d. So therefore mu d r, this will be 1 by mu, here d and here r. It will be just the reciprocal of this. So therefore it will be 1 divided by root of 2 by 3, which is nothing but root of 3 by 2. That will be the answer of refractive index of the dense medium with respect to the rare medium. That is what is asked also. Is that clear? Hi Hazu, welcome aboard everyone. Now the second part, finding the ratio of the wavelengths. That is also something which we can easily do. Just use this relationship. See guys, we just got mu dr, right? Mu dr, d mu r, okay? This was root 2 by root 3. Remember, this will be also equal to wavelength in the first medium upon wavelength in the second medium. It was going from dense to rare, first to second. So same order will be followed in wavelength also. So this value we already know. This was root 2 by 3. This was root 2 by 3. This wavelength in the dense medium was 2000. So this was 2000. This is in the rare medium. So therefore, wavelength in the rare medium will be 2000 and root 3 will be on the top and 2 will be below. So if you want, you can cancel root 2. So it will become 1000 root 2 into root 3. 2 3s are 6. So it will become 1000 root 6 Armstrong. That's it. So that is the wavelength in that rare medium. That's the answer. Okay. Is there any test series for NEET? Sriram, we are planning, and if there is, definitely will be announced on the NEET English channel. Okay, Sriram? Great, perfect. So let's go to another question coming up on your screen, and here it is. Imagine there is a sphere. Imagine there is a sphere like this, and this is a normal at one place. And what happens is light is entering over here, okay, at a certain angle, and it refracts over here. And again refracts over here. Two times refraction is happening over here. It so happens that the refractive index of this medium is root 3, and this particular angle which you see over here happens to be 60 degrees. Question is, find the total deviation. Find the total deviation. Think as if this entire circle which you see is some kind of glassy, soapy, whatever, drop of some liquid, or maybe some translucent jelly-like material, something it is. And light is entering into one region and going out from the other region. Question is, figure out what is the total angle by which the light ray has got deviated. Okay. Now, let's see what we should do. Ananya, which part of that previous question? I'll just explain this once more in case you had some query. Here the light was going at 45 degrees, it deviates 15 degrees away. That is why I have shown it go like that. And that is why I know this will be rare, this will be dense. Light was going from dense to rare. That is very clear from the question. Because this is 15, if this is 45, this is also 45. So the total refracted angle is 60 degree, because this much is 60, sorry, 45. This much is 15. So 45 plus 15 will be 60 degree. So because I know incident and refracted, we can easily find the relative refractive index. But whatever I get will be from dense to rare. But the question asked is rare to dense. So because it was rare to dense, I took the reciprocal, which is a standard formula. So instead of root 2 by 3, I took root 3 by 2. That is first answer. For the second answer, I will say that when light goes from one medium to another medium, the wavelength will change. And the wavelength formula, I just gave it to you right over here, isn't it? Yeah. 1 mu 2 is lambda 1 by lambda 2. This was the formula. Wavelength will change, frequency will remain unchanged. So that's all I have done over here. 1 mu 2 is lambda 1 by lambda 2. DDRR 1 1 2 2. So this value I know, this is given. Rarer medium wavelength is not given. So just rearranging it, we get the answer. Only thing is root 2 and root 2 will get cancelled. So 1000 will remain. 1 root 2 will remain on the top, multiplied by root 3. So that will become root 6. I hope it is very, very clear now. Okay. Now, I hope Ananya, it's fine. Now, here, what we can do, we can say the light will deviate here also and it will deviate here also. So, as you can see, there is some amount of deviation here, delta 1, and there is some amount of here, which is delta 2. So, if you ask me the total deviation, should it be delta 1 minus delta 2 or delta 1 plus delta 2? As you can see, the light is turning towards the clockwise direction. Here also it is turning towards the clockwise direction. So first time it turned here, second time it further turned here. So the total deviation, as you can see, is the sum of both the angles. So that's why this should be plus. But I do not know what delta 1 and delta 2 are. So I'll think about it in some formula now. Okay. So first of all, this will be the angle of refraction. And if this is R, can you see this small isosceles triangle form? This is radius. This is also radius. So if this is isosceles triangle, the base angles will be same. So that is why this will be also R. This will be also R. It is very obvious now. Now if this is R, by reversibility principle of light, think about it. If light enters at 60 and refracts at some R, if light is now refracting at R, reverse it, that angle of incidence over here, this particular angle will be obviously 60 degrees. It's just mirroring. If you just change the direction of light, if this is 60, this will be R. Okay? It's just reversibility principle of light. Makes sense? You can just change the direction of the arrow marks. The lines will remain the same. The ray diagrams will remain the same. Only the directions will change. So all the angles, everything will be the same. So I got to know that the base angles are same. Great. Can I find those base angles? Because only then I can find delta. Yes, we can use Snell's law. So sine of I divided by sine of R is light is going from vacuum to that particular medium, whatever that medium M is. So I'm just putting that. Okay. So sine of 60 degree by sine of R, which I do not know. The relative refractive index is root 3. So sine 60 is root 3 by 2. Okay. And this is root 3. Sine R, I will take it on the top. As you can very nicely see, this root 3 and this root 3 went off. So sine R is half. So sine R is half means R is nothing but 30 degrees. That is quite obvious, isn't it? Whose sine is half? Sine 30 is 0.5 or half. Once I get R, we can find delta 1 and delta 2 easily. So clearly, delta 1 will be I minus R. So it will be 60 minus 30, which is 30. Whereas delta 2 will be R minus I, or basically that is refracted, this is incident. Again, it's the same thing. It will be 60 bigger angle minus smaller angle. So again, it will be 30 degrees. So both of them are 30 degrees. This much is 60 minus 30. Even this much is bigger angle minus that smaller angle, which is 30. So again, you are getting it as 30. So 30 plus 30 is 60 degrees. So the total deviation is 60 degrees. Perfect. Everyone, very straightforward question. And you can see laws of refraction are applicable not just for flat surfaces, but even curved surfaces. So wherever the light is getting refracted, that part I can assume it as flat. Only that part I can assume it as flat. Okay. Let's go to another question coming up on your screen. Here it is. This was a previous year question of J. Light is going from air to some medium at 45 degrees. After refraction, I think. Oh, I just did this, no? The same question. My bad. It refracts 15 degrees away from the normal and has some wavelength. By mistake, I did it. Anyways, that's the same previous year question. Maybe you can do it as homework. Okay, so try this as homework. You should be able to do it. It's the same thing anyways. Okay, going to the next question. A light of some wavelength and some frequency is entering some other medium. The incident and the refracted angles are 45 and 30. Wavelength and the frequency are, come on, what do you think? Let's draw it in case you are confused. So this is the surface. This is the normal. Okay. Incident is 45. Refracted is 30. Incident is 45. Refracted is 30. Okay. So light is going like that, like this. This is 45 degree. This is 30 degree. It's obvious that this is dense and obviously this will be rare medium. Okay. What about the wavelength and the frequency? First of all, frequency will not change. Frequency, whatever it is. Okay. Frequency. Frequency remains the same. Yes. So frequency will remain the same. So V2 will be mu1 or yeah, this one. Only one of these options will be correct. Is that making sense, everyone? Nu1 and Nu2 or F1 and F2 will be same. It will not change. I just told you because it only depends on the source. Okay. Now the only part is the wavelength part. So for that, light is going from the first medium to the second medium. So this will be nothing but sine of I, which is sine of 45 degrees by sine of R, which is 30 degrees, which is wavelength in the first medium, which is lambda 1 by wavelength in the second medium. So sine 45 is 1 by root 2, sine 30 is 1 by 2. So that will be lambda 1 by lambda 2. So this will become 2 by root 2, which is same as root 2 is lambda 1 by lambda 2. So therefore, lambda 1 is root 2 times of lambda 2. Lambda 1 is root 2 times of lambda 2 or lambda 2 is 1 by root 2 times of lambda 1, which is right over here. So hence the correct option will be option B or option 2. Okay. This is again directly application of formula. Gojo, I'm very good. I'm very good. Thank you so much, guys. I hope you guys are also doing great. Quickly smash the like button in case you haven't done that already. Okay. Shall we go to the next question, guys, coming up on your screen? This is also a very famous question. You might have seen this as a good level of question in many places. Okay. Read the question, guys. Read the question carefully and say what is asked in this particular. Hmm. Okay. So observer can see through a small hole on the side of a jar and what is there? Height is also given 15 centimeters from the bottom, a hole of height 45 centimeters is made. Okay, when the jar is filled with some liquid till 30 centimeters, the same observer can see the edge at the bottom of that particular jar. The question is, uh, figure out what is the value of the refractive index. So this is 15, this is 45. Okay, so if you think of some geometrical construction, that will be better. See, oops, draw horizontal line like this. If this is 45, this is 15, it is obvious that this much, only this much will be 30. Okay, this much will be 30. This will be, this will be 45 minus 15, that will be 30. And this is 15, this is also 15. So that also tells one more thing. If this much is also 15, not just the height, even the width, okay, even this, which is the radius of that cylinder or the container, that is also going to be 15. So clearly it's a symmetrical diagram. So this will be exactly at the midpoint. Okay, so the light is going exactly at the midpoint. I can construct, one geometrical figure like this. Yeah, I can construct one geometrical figure like this. This and this will also be equal. Okay, this and this will also be equal. So this is one triangle which will be again equal to another triangle right over here. Another over here. Both these triangles will be congruent. One thing is very, very obvious. And because this is 15, this is 15, this is all our congruent triangles, even this will be 15. Yeah, even this particular height will also be 15. This particular height will also be 15. It's very obvious. It's clearly mentioned the liquid is filled up to 30 centimeters. So 15 is already this much. This is extra 15. So total height is 15. That means the liquid, whichever is there, that liquid is exactly filled till this particular point. So these are some conclusions which I have drawn just purely based on geometry. I didn't use one bit of optics till now. This is purely, yeah, geometry, nothing else. Clearly, as per the question, it is mentioned when you make this hole, earlier you were able to see this point which is 15 centimeters above. Now, when you fill that liquid, then the observer can see the edge of the bottom. That means this edge, which means this light ray is able to travel like this. This light ray is able to travel like this over here. So that is the final ray diagram. So this particular light ray is going like this. This is my object. And finally, the light bends and comes over here. Okay, this much fine till this particular point. Now we need to think about what is the refractive index. So for finding the refractive index, let me mark the angle of incidence and refraction, obviously. So due to the reversibility principle of light, I am okay with changing the arrow mark, whether I take it like this, whether I take it like this, or whether I take it like this. It really doesn't matter. If light goes like that, it will come out from here. If it is coming here, that means light would be entering like this. So reversibility principle of light allows me to make anything as, the first medium. So usually we take the outside medium as the rarer medium, which is the first medium, so that it is easier and it is based on our past experiences, right? Like that is what we have been doing. So it will not sound very strange or look very strange. So let's continue with that. Okay, so this is the rarer medium, this is air. So obviously this will be angle of incidence. This will be angle of incidence. Naturally then, this will be the angle of refraction. This will be the angle of refraction. Now how much these angles are, we can find it out, not a big deal. See guys, if this is 15, okay, I can just construct one triangle like this over here, and I can think of another triangle like this over here. Now it becomes easier for me to see. If this is R, okay, this side length is 15, this side length is 30, here this is 15, and this is also 15. So I think we can figure out what I and R is just from this. What I and R is just from this. Like over here, because both are 15, it's very obvious that incident angle will be 45 degrees. Or you can just say that tan of I is opposite side by adjacent side, which is 1. Therefore, incident angle is 45 degrees. Is this much part clear? Everyone with me? Why incident angle is 45 degrees? Very good. Very good. Excellent. Now coming to the next part. What about angle of refraction? Well, see, if this is 30, this is 15, the hypotenuse, that is this side, will be root of 30 square plus 15 square. Why I'm doing that? Because I need sine R. So sine of R, because R won't be a standard angle, I can sense that very easily. So sine of R will be opposite side, which is 15, divided by hypotenuse, which is nothing but root of 30 square plus 15 square. Here I did not do sine because it's obvious that I will be 45 degrees, sides were equal. Okay, it was very obvious. Here it is obvious it will not be a standard angle. So this will be 15 plus, okay, 15 can be taken common outside. So 15 square, and this will be 2 square plus 1, the whole thing under the root. So that will make it 15 by 15. 2 square is 4, 4 plus 1, which is 5. So it will become 1 by root of 5. That will be sine of R. Now we can find the refractive index. Light is going from vacuum to that medium, whatever. So it will be sine of I by sine of R. Sine of I, that means it will be sine of 45 degree divided by sine of R, which value is directly given or found as 1 by root 5. So root 5 will go on the top. Sine 45 is 1 by root 2. So root 5 by root 2, but root 5 by root 2 is nothing but 1.58. It is already mentioned, 1.58. But it is mentioned that the refractive index is n by 100. So this value is already given to be n divided by 100 as per this information. So therefore, n will be 100 into 1.58, which is 158. So hence, the correct answer will be 158. Yes, 158 is the answer. So this kind of question can come as a numerical type of question. Okay, pure geometry. I mean, look at it. Till here, it's just geometry. Only this much part is ray optics, which is that too so simple. Got it? So usually in ray optics, right, lenses, mirrors, these kind of questions, many times you will see the questions, especially the complicated ones, involve geometry, trigonometry, properties of triangle, circle, square, whatever, straight lines, parallel lines, and that optics part will be usually minimal. Like this was also geometrical problem. Even, what do you say? Even this was a geometrical problem, if you see. Lot of geometry, isosceles triangle, base angles are equal, all of that. So majority of the times you will see geometry plays a important role. Okay. Now let's go to the next concept, which is the concept of total internal reflection. Apparent depth will come later on. I think the slide by mistakenly came here. 1 second, guys. The concept of total internal reflection. Okay, total internal reflection. All right, gravitation also coming after rotational motion. Okay, so we'll have to wait for rotational motion to be over, then we'll make gravitation. See, when light goes from rare to dense, it bends towards the normal. But when it goes from dense to rare, it goes away from the normal. So imagine this to be a denser medium. this to be a denser medium, and this is obviously a rarer medium. So if a ray is going here, it will definitely bend away from the normal. Bends away from the normal. It bends away from the normal. Now, if you increase the angle of incidence slightly, it bends further away from the normal. If you increase it so much that it is almost grazing the surface, this phenomena is called as grazing the surface of that medium, grazing the surface of that medium or grazing the interface. Then you will see a special case where angle of refraction is 90 degree. Then this particular angle is called as that critical angle of incidence, IC. It is called critical incidence, critical incidence, because that is the maximum angle which you can keep inside the denser medium, because anything beyond that will no longer be able to come out in the other medium, this ray, because the angle of incidence is more than the critical angle, you will see it will get reflected inside instead of refraction. All these places, at all these places, you are seeing refraction happening. Refraction happening. But over here, what are you seeing? It is getting reflected. It is getting reflected. So it is getting reflected not because there is a mirror here, but because of the manner of the refractive indices and Snell's law. So this is then called total internal reflection. Totally, it is getting internally reflected in the denser medium. Got it, everyone? What is this concept of total internal reflection? It can only happen when light goes from dense to rare. From rare to dense, it cannot happen. Please remember that. So as you increase the angle, finally comes a point where the light cannot further refract. So it has to come inside. But when it comes inside the same medium, then it is no longer called refraction. Then it will be reflection. So all the light will just get purely reflected. Nothing will get refracted. Cool. Okay. So what is the angle at which the light refracts critically? So that critical angle of incidence. Okay. So let's understand that. This particular angle, which is basically IC. And obviously this is angle of refraction, which is 90 degree. Okay. Now usually the outside medium will be called the first medium and the inside medium will be called the second medium, or we can call it like this. This is usually your rarer medium. This is your denser medium. Like this is air, this is glass, this is vacuum, this is water, like that. So if you use Snell's law directly, then first angle sine into refractive index. So mu d into sine of that particular critical angle will be sine of that second angle into that refractive index. So sine of r multiplied by that what is it, mu of that rare. So this is 90 degrees, so this is sine 90 multiplied by mu r. Sine 90 is 1, so 1 multiplied by mu r. So this is mu d multiplied by sine of IC. I will take mu d below over here. I'll take mu d below over here. What is this going to be? What is this going to be? Mu r by mu d. This is relative refractive index. This is relative refractive index. Where did the light go? It has gone from the dense medium to the rare medium. Mu d mu r is mu r by mu d. But usually this is not given to you. The exact reciprocal will be given to you. So this is the same as mu d over here, r over here. That means when light goes from rare to dense. So like refractive index of glass with respect to vacuum. So, light is going from vacuum to glass. That is what is usually given to you, not the other way around. So that is why it is better to remember this particular formula. Think like this, guys. This value should be more than 1. whatever on the right hand side should be more than 1, because LHS is less than 1, my bad, because sign value is always less than 1. So if this value has to be less than 1, this has to be less than 1, the reciprocal, when you take it, this will be a number like 1.5, 1.7 and 2.5, like that, so that the reciprocal comes out to be less than 1. That is why we put that refractive index in the denominator. Okay, think of it mathematically, why it makes sense. Because sign values are always less than 1. So refractive indexes are like 1.5, 1.6, 1.33. So you'll put it in the denominator so that the ratio becomes less than 1. Clear? Yes. Awesome. So cool. Sir, I'm studying in class 9th. Will this be useful for you? Yeah, definitely. Why not, Dr. V? These things are very basic. And if you attend any NSEJS or even the basic Olympiads, the first level, many times these concepts are only there. Ray optics, kinematics, Newton's laws, gravitation, basic electromagnetic induction, electricity, magnetism, current, electricity, right? And some basics of modern, all these things, right? Critical angle more than 90, not possible. Yeah. Okay. Critical angle cannot be more than 90, right? So keep that in mind. Okay. So that's pretty much about it. So I think we can start with some questions coming up on your screen. Here it is. The critical angle of incidence for a pair of optical media is 45 degree. Then the refractive indices of first and the second medium are in what ratio? The critical angle of incidence for a pair of optical media is 45 degree. The refractive index of the first and second are how much? Okay, so what it says is, see, we have a surface. Okay, this is the normal, and light is going like this and like this. This is critical angle refract first and the second. This is mu1, this is mu2. Obviously, this is going to be dense, this is going to be rare medium, and it is mentioned that finally when you increase the angle to 45 degrees, it becomes critical. So when you make it 45 degrees, the light will come grazing like this, almost here. So this is going to be 90 degree, and this is going to be your critical angle, which is 45 degree. That is what is mentioned. Otherwise, the light will come out only at critical angle. It grazes the surface. After the critical angle, it internally reflects in that same medium. Okay, let's understand now. What do? We know that sine of critical angle is 1 by refractive index, right? Light going from rare medium to the denser medium. But this is the same as mu d over here and r over here. This is same as mu r divided by mu d. 1 mu 2 is nothing but mu 2 by mu 1. Okay. Over here in this particular context, critical angle is 45 degrees. See, I'm strictly following the rules. I'm not getting confused. Okay. If you do some weird calculation, mental math and mental visualization, you will definitely get a wrong ratio. Critical angle's value is 45 degree. Rare medium is mu2 over here, and the dense medium is basically mu1 over here. So sine 45 is 1 by root 2 is mu2 by mu1. That clearly means mu1 by mu2. Mu1 by mu2 will be root of 2 is to 1. So root of 2 is to 1, which is option number 1. Option number 1. That is the correct answer. Clear? So very simple. If you follow the rules, if you know it properly, you can get the answer. Else you will be confused. Sir, rare, dense, who is what? What is... So then many people get confused between option 1 and option 3 because they are very similar. You can definitely make a silly mistake in the exam. You only think and tell me. Isn't it possible? There is a more than 50% chance that many kids will mark option 3 because they got confused between this and this. And definitely there is a high probability of making that mistake. Yes, King of Kings. That is the correct answer. Very good. All right. I would love to see you more, Dr. V. Rama. Yeah. because you're preparing for Olympiads. So I would love to have you. Okay, we'll solve one more question, guys. Let's solve that. Just get rid of this. So this is also a very good question on critical angle of incidence. So what happens is, you might have seen that, let's say this is the water surface. This is the water surface. Okay, there is some water inside, and maybe somewhere deep inside this particular liquid, there is a light source. There is a source of light. That source of light will emit light rays in all the possible directions. Maybe one of those light rays, will go like this, perpendicular, no deviation at all. Another light ray will come over here. Maybe because it is going from dense to rare, it will bend away from the normal. Another light ray will come over here, bend further away from the normal. Okay, same thing over here also, it comes here, bends away from the normal. It comes over here and bends further away from the normal until it reaches a critical state right over here, where it is almost like grazing the surface, because after that, whatever light rays will come, they will not be able to come out. They will just get internally reflected. They'll just follow the laws of reflection. They'll just get reflected. So this ray also will get reflected internally. So this is your total internal reflection. This particular one was grazing incidence. Before that, all the light rays were getting refracted into the other medium. So if there is a point source, there is a distance from that central line where the light rays are able to come out. Beyond that, they are not. And this is just a two-dimensional figure. But imagine this in three dimension. This will definitely become a cone-like structure, where probably it will look something like this, with the light from the source coming out this way, and this particular thing like this. This will be the central one, and over here like this. Visualize this. And this will be your liquid surface. See if you are able to visualize. This is how it will be. This will be the water surface. This I have shown it in 3 dimension. That's all. Okay. Every other place there will be rays coming out, except for beyond this point. And if you visualize it in 3 dimension, it will form like a conical structure. Are you now able to visualize it? It will form a conical structure. I want to find what is the radius. I want to find what is the radius. I want to find what is the radius of that particular cone through which the light will emerge and beyond which the light won't be able to emerge. This is a very famous question. Okay. Rotational motion after circular, next lecture. I mean, this Wednesday only we are doing circular motion, which is the pre-foundation, I would say, for rotational motion. So once circular is over, we continue that same thing with rotational motion, because center of mass is done, momentum and collisions is also done, king of kings. Okay. So we'll continue with the same streak. So how do we solve that question? First of all, let me think of the extreme rays. See guys, this is that liquid surface, isn't it? Okay, let me redraw it. This was that liquid surface. Okay, this was the light ray which will go undeviated. The extreme ray which will go critical incidence will be like this over here. Then it will go like that. Okay. Now let me draw normal over here. Okay. So this obviously will be the critical angle. This line and this line are parallel. So this will be the critical angle. It's obvious. The question was to find the radius. So this will be the radius, and the depth at which the source will be present is, let's say, h. So from this you can see this is h, this is r. So this length will be root of r square plus h square. Now, since sine of critical angle will be usually given to me, which is 1 by that relative refractive index, this sine is opposite side by hypotenuse, which means it will be r divided by r square plus h square. So this is 1 by mu, square both sides. So r square by r square plus h square is 1 by mu square, cross multiply both sides. So r square mu square will be r square plus h square. Bring r on one side because we want it. So r square into mu square minus 1 is equal to h square. So therefore r square will be h square divided by mu square minus 1. Therefore r will be taking root on both sides. h square's root is h. The whole thing divided by root of mu square minus 1. That's the answer. H divided by root mu square minus 1. This problem has come multiple times in JEE Mains, so you cannot afford to skip it. Okay. Megsai, how about this? Put up that comment in the comment section, not just in the live chat. I will get back to you. Okay. Reason, I want everybody to read that comment, whatever I will answer, because you asked a very good question. So I'll reply to you in the comment section. Cool. After the video is over, not in the live chat, Megsai. After the video is over. Okay. High weightage chapters, Anjali, I have already given. Please check out my previous weightage videos, 25% syllabus, 99 percentile marks. I've given the list of all the topics. Multiple times in the last 2 weeks, I have made that video. Please check that out, Anjali. Okay, it's there on the channel in the live section only, not videos, live section. All right. Okay, great. Now, let us go to the next concept, which is apparent depth. This is very interesting thing, and you would have sometimes seen a swimming pool or a swimming tank where you used to swim. When the entire water gets cleared out, you see that the floor of the pool is suddenly so deep, and you used to think that, oh, it's not so deep when you look at it normally filled with water. But actually the swimming pools are very deep. You don't feel that depth once liquid is filled inside it. This is that notion of apparent depth. Whenever you are in a rare medium like this eye, the observer is in a rare medium, and that observer sees something immersed in a denser medium, like the base of the swimming pool. The observer will find that the rays are actually emerging from a point much above it. So you will find the depth to be much shallower than what it actually is. So if the observer is in a rare medium, and the object which is seen is in dense medium, I is basically, that is the location where the image is formed. This is where the image is going to be formed. This particular depth which you are seeing over here, versus this depth, this is apparent depth. That means what you feel like. But this is D, which is your actual depth. This D is your actual, real depth. Actual or real depth. This is what you feel like. So the apparent depth is always shallow. The apparent depth is always shallow because of the manner in which the light rays go. Look at this. This light ray will bend away from the normal. So if you extend that ray behind, the image will be formed here. So the rays are going in this direction. So when extrapolated behind, the eye will or the brain will perceive that rays to be coming from here, not from here, because they are going like this, not like that. So that is the perception which is developed in the brain. Okay, really the object is here, but virtually this is a virtual image. Yes, this is a virtual image which is formed. This is a virtual image which is formed, which is slightly shallower than the real one. The same thing is true for the exact reverse scenario. The same thing is also true for the reverse scenario. Hi NSP, Tharun, I'll definitely conduct marathons, but you are free to check out my older marathons for CBSE. It's there on the channel. Just search for CBSE marathons or CBSE Shreyas sir. You will get it on the YouTube platform. If imagine this is the surface and the observer happens to be in the denser medium. The observer is seeing something which is flying in air, maybe a bird. Yeah, very nice bird, cool looking bird. It's a cool bird which is flying in air. This is where the object is. This is where the observer is. And the image of this object is formed over here. This is where the image is formed. This is now apparent. This is now apparent. Here it is more, okay, this is D prime, than the actual one. This is actual. This is actual one, which is basically D. The apparent is more than the actual in the reverse scenario when the observer is in a denser medium. Is in denser medium. Whereas the object is in a rarer medium. Object is in rare medium. Exact reverse. So if a fish sees a bird, the bird will look very far away. But the same bird, when it looks down at the fish will appear closer than it is actually. Very cool phenomena. And imagine the dynamics which will go on in the nature when the bird, like kingfisher, is trying to hunt, a fish. The bird is feeling like the fish is very close to the water surface. The fish looks at the bird thinking, oh, it is very far away. And when the bird dives into the water, thinking the fish is over here with its claws, it will miss the fish because the actual fish will be here. And the fish, which is here, when it sees the bird suddenly coming so close, it will get freaked out, thinking, oh, I thought the bird was very far away. How the hell did it, come out so close? So that is how the dynamics will play out. Okay, that's the concept of apparent depth. So in the first scenario, basically when you're talking about depth, so apparent depth will be actual depth divided by the relative refractive index of the denser medium with respect to the rarer one. That's it. So, if it is depth related concept, it will be just this formula. This is the relative refractive index. But when it comes to the exact opposite, the apparent height will be more. So apparent height will be actual height multiplied by the refractive index of that dense medium with respect to the rare medium. So H prime will be H multiplied by that relative refractive index. So better to use the same symbol here also and not confuse you. So this is H prime and this is basically H, the actual height. So whenever it comes to height, multiply. Whenever it comes to depth, divide it. Okay. D for dive, denominator. H for height, numerator. Okay. So very easy looking formula. For height, it will be more, it will be farther. So multiply with a number more than 1. For depth, in the denominator, divide it with a number more than 1 so that d prime will be less than t. Very simple. Okay, cool, perfect. Let's see some questions coming up on your screen. Here it is. There is an ice cube which is having a bubble inside. When seen from one side, the distance apparently is 12, but on the other side, the distance is 4. So if the side of the ice cube is 24, the refractive index is how much? Very good question, guys. So let's try to understand. So this is that ice cube. Okay. First time, the observer is over here. This is the observer. What is the observer seeing? The image is formed over here. Image is formed here. The actual object is somewhere here. I do not know where. And this image is formed at a depth of how much? From front side, it is seen to be 12 centimeters. 12 centimeters. What is the actual depth? I do not know. I'll just call it as D1. I'll just call it as D1. So observer is in the rear. The actual object is in the dense. The object will appear to be closer to the surface. Closer to the surface. The second scenario. The observer is on the other side, still in the rarer medium. This time, the image is formed over here, I2, and this distance, whatever it is, comes out to be how much? 4 centimeters. This is 4 centimeters. But from this side, how deep that object is, that I don't know. I will call it as D2. This is the figurative explanation of the entire passage. Check this out. This is what the actual question means. Now, because every time the object, the actual object which is there, is in the denser medium always. So, which formula will you use? Which formula will you use? This one or this one? Object is in the denser medium, appears closer. So, depth concept. So, it is this formula which I have to use. So, apparent depth. So, I have to use basically apparent depth is nothing but actual depth by relative refractive index. So, for the first scenario, I can say the apparent depth is 12, the actual depth is D1, relative refractive index I do not know. But wait a minute, do I know D1 and D2? Maybe. An ice has a cube inside. When viewed from the other side, oh, I do not know that D1 and D2 separately. Second time, by the way, from this I'll just get D1 is equal to 12 times of mu. Second time, I can say that apparent depth of 4 is that real depth of D2 divided by the refractive index. So D2 will be 4 times of mu. Now I have an idea. What if I add D1 and D2? Think about it. If I add D1 plus D2, I should get the entire side length of the cube, which is 24 centimeters, which is 24 centimeters, isn't it? So D1 plus D2 is 24. So this is 24. But wait a minute, I already know D1. D1 is nothing but 12 mu. I know D2, which is also 4 mu. So 12 plus 4 is nothing but 16 mu is 24. Therefore, mu is equal to 24 by 16, which is divisible by 8 3 times. This is 2 times. 3 by 2 is the answer. So option labeled 2. The second option is the answer. Is it clear? Very straightforward. Yeah, very nice question. Many people think, sir, I don't know D1, D2, how do I solve? Hold on, have some patience. As you solve the problem, you'll get to know what else equation can you use. So the critical equation was this, where if you add the distances, the real depths together, you will get the total side length of the cube. Side length of the cube. Is that clear? Very good. Perfecto. Let's look at another question coming up on your screen. Wow, what a colorful, good looking question. I love this question. If the actual height of a bird and the actual depth of the fish from the free surface of the water is 36 meters each, find the apparent height of the bird. At what distance will the bird appear to the fish? Find the apparent depth of the fish. At what distance will the fish appear to the bird? Very simple looking question, guys. What do? Start off with the bird first. The apparent height will be actual height multiplied by mu. Relative refractive index is 4 by 3 only. It's obvious. The actual height is 36. So multiplied by the relative refractive index, which is 4 by 3. 36 by 3 is 12. 12 4s are 48. So this will be 48 meters. So the bird will appear 48 meters away from the free surface. Very straightforward. Similarly, let's look at this. Apparent depth. Apparent depth is actual depth by mu. Actual depth is 36. Mu is again 4 by 3. Mu is again 4 by 3, isn't it? So that's it. Use it. So 36 multiplied by 3 divided by 4. 4 goes with 36 9 times. 9 3 is a 27. So 27 meters. So instead of 36 meters deep, the fish will appear only at a distance of 27 meters. 27 meters. Such a colorful question, isn't it? Yeah, loved it, guys. Perfect. Very cool. Very cool. Now, let me give you one more thing over here. Imagine this is the liquid surface and there is some bird which is moving towards the free surface at maybe 6 meters per second, and this fish is diving up at a speed of 12 meters per second. Refractive index is 4 by 3. Question is, find the relative speed of the bird with respect to what the fish will see. Find the relative speed of the bird as seen by the fish. As seen by the fish. These kind of questions, you need to be very, very careful. Are you going to see apparent height or apparent depth? You need to understand that first. Because the observer is the bird, observer is the fish and the object is the bird. So the bird will always appear to be farther away. The bird will always appear to be farther away. So the apparent height of the bird will be actual height multiplied by mu. Now, imagine I differentiate this equation. What? Why differentiate? Because velocity is there and velocity is the relative, it is the rate of change of distance. So think about it. If this was h, if this is h, what will be dh by dt? Rate of change of this height from the surface. Rate of change of this height from the surface. So therefore, can I say if I differentiate dh by dt, this is mu is a constant. This will be dh prime by dt. Okay. Now I have differentiated this, both sides. This dh by dt is basically the actual speed of the bird. Refractive index 4 by 3. This is nothing but apparent speed of the bird. So 6 by 3, 2, 2 4s are 8. So 8 meters per second. So the relative speed of the bird is 8 meters per second, but be careful, it is with respect to the interface. This is the most common mistake which many kids do. This is always measured from the interface, but the interface itself is coming closer to the fish. Interface itself is coming closer to the fish. The bird is also coming closer to the interface. So think like this. The bird's image, this is bird prime, is coming at 8 meters per second closer to that interface, and at the same time the fish is moving up with a speed of 12 meters per second, the real fish. So everything measure it from the frame of reference of the interface. So the frame of reference is now your interface. Bird is coming with 8, the fish is coming with 12. So what will be their relative speed? So that is exactly what is asked. So the answer is the relative speed of the bird with respect to the fish. That will be simply addition of these two because they are moving in opposite directions. 8 plus 12, which is 20 meters per second. That is the answer. 20 meters per second. Got it? So this is a good level of question. Many students just leave the answer at 8. They forget to add this. Then they get confused whether to add them or subtract them. That you need to think. If both are moving in opposite directions, it will be addition. If it is the same direction, it will be subtraction. Simple. Correct? Okay. Let's move now to some another kind of questions, which is lateral shift and you know this kind of things, lateral shift and then multiple slabs and all of that. These are the only two things remaining. Okay. First of all, if you have a glass slab and the light is falling perpendicular to the slab, that light ray will go undeviated. So whenever it falls perpendicular, the emergent ray is undeviated. Undeviated, and there is no kind of any shift, no shift in the ray. The ray continues the same path because angle of incidence 0, angle of refraction 0, angle of incidence 0, angle of refraction 0. Many of you are thinking, sir, angle of incidence is 90, but let me remind you, angles are always measured with the normal. So the ray is technically making 0 degrees. It's not 90 degrees. Okay. So the ray will just continue. But if the ray is making some angle, then things change. In fact, it is very evident here that as the ray enters, it will get refracted. Instead of continuing its journey along this path, it is now going here and then coming out from here. This emergent ray is parallel to the incident ray. The emergent ray is definitely parallel to the incident, ray. So technically the angle of deviation is 0 degree. The light ray has not deviated its path, but it has shifted. It's like two trucks or two cars, two buses moving parallel. Earlier one bus was going like this, and behind that another bus was following it. Then the bus behind moved like this and came on the side, and now they are moving parallelly. So there is no deviation angle wise, but there is a shift. It's like the bus has gone to the next lane or the car has gone to the another lane. Correct? So this particular distance that you see, that particular distance d that you see, that is called as lateral shift. That is called as the lateral shift. And you would have seen that you hold a glass slab in front of you, suddenly you feel that the thing has shifted somewhere. You will feel that suddenly it will shift somewhere. That is the concept of lateral shift. Okay, everybody with me on this? Pakka? Everyone? Okay, perfect. So you might be wondering, sir, what is the formula for this lateral shift? You can get it using simple geometry and all of that. You have to just use that geometry on this particular triangle and just do some geometrical constructions over here. Like this is the thickness of the slab, all of that. This is thickness of the slab. This is the thickness of the slab. T. This is 90 degree, and then draw a line here, all of that. And from that, you can easily get what that shift is. It's not a big deal. I mean, if I call this line from here to here as the hypotenuse, okay, so from this you can get this particular length, and then again you have to use trigonometry in this small triangle, and then you can get that answer. It is not such a big deal. So the final answer, I'll tell you what you get is this: D is equal to the thickness of that slab into sine of angle of incidence minus angle of refraction, whole thing divided by cos of angle of refraction. That is the formula. This formula, please remember, direct questions come. In fact, I think there is a question which I have put. Yes, this year there was a question on what the formula is. Forget even substituting. Directly that formula came. And the answer was very simple: h sine I minus r by cos r, where h was the thickness of the slab. So such direct questions also come. Sometimes value-based questions, substitution have come. Sometimes direct formula. Soham, no man. After this, there are at least 3 classes of ray optics. It's a big chapter. It's a unit in itself. So some of you are also wondering, can I have the derivation of it? The derivation also is put over here just in case you need it, because the formula came directly. Okay. So that is one small concept which I had to tell you. So I'm just telling you that. Now, the last concept, which is of multiple slabs. That's what we are going to see. Multiple layers, multiple medium changes. So what are the different things that you need to remember? Rajit, I'm so happy and glad for you. I think you were one of our students, but I don't remember your name. Maybe uh, because so many kids are over here, but I'm so glad that you have made it through and you came back to just mention that. That has made my day, I would say. Very good. Congratulations. And you can tell your juniors also which college or which stream you are going to, what do you aspire to become. And I'm pretty sure you're all excited for meeting new people, meeting your new mates and professors, and seeing the college campus and enjoying. Okay. All the very best, my dear. Okay. So when there are multiple layers, then this refractive index, instead of N1, N2, I don't like that number N1, N2. So I'll just make this as like this. So say this is mu1, this is absolute refractive indices, mu3, mu4, mu5, etc. Then if I use Snell's law for all these pair of media, I can write it as sine angle made in the first medium into refractive index of the first medium, sine angle made in the second medium into refractive index of the second medium, sine angle made in the third medium into refractive index of the third medium. Like that, whatever, how many ever terms are there? Sine angle made in the nth medium into refractive index of the nth medium. So basically, I can say sine theta multiplied by mu is a constant. That is what you will get whenever there are multiple mediums. You can use this like a property wherever you want. Wherever you want. Very interesting. Now, there is a very interesting finding of this. Just imagine this. Giving you an example. There was a medium here. Okay. And same medium is here. In between of that, there are different mediums. One is this, one is this, maybe another is this, and all of it. Then same two mediums are there. Same two mediums are there. And again, you have some another types of mediums. One medium is here, and another medium, sorry, one medium is here, and then maybe another medium is here. Sorry, then maybe another medium is here, like this. Okay. The point is the first and the last medium are same. You will see if the light ray has entered into this medium like this, it will emerge out parallelly here, irrespective of how many mediums and which mediums are there. Doesn't matter whatever is there in between because of this law. Because sine theta into mu is constant. Whatever theta is here, whatever mu is here, same mu is here, so theta should be same. So whatever is in between doesn't matter because their product is constant no matter how many terms you keep in between. The first term and the last term will be the same. So if the medium are same, whatever is in between doesn't matter, the ray will end up with the same angle. This is the beauty of this property. Okay. Thank you, Jayavant. Means a lot. Okay. During my time, we did not have JEE Mains, nor did we have the concept of percentile. We had IITJEE examination, which is like your JEE Mains. That time we used to have JEE screening to write JEE Advanced. But that time JEE Advanced was called JEE Mains, but the level was JEE Advanced. And the JEE Advanced paper was not computer based, rather it was paper based and subjective paper. So I have written both examinations, IITJEE, which is for NITs, GFTIs, everything, and private colleges, and IIT screening, which was level 1 exam, and then JEE Advanced examination to get into IITs. So we used to have two separate exams, and those things slowly got scrapped, and then they got merged and everything. I wrote the last subjective paper of JEE Advanced. Okay, great. So, sir, tell me one thing. Will there be a concept of apparent depth here also? The answer is yes. The answer is yes. Because there are multiple layers. Imagine there is an observer here and something is deeply inside over here. Then that object will appear somewhere else because of multiple refractions. Now, usually our apparent depth used to be actual depth by mu. But since there are multiple layers, there will be multiple terms here. And what will happen now? It will be first width or first depth into that refractive index plus second depth into second refractive index, like that. So the net apparent depth, the net apparent depth will be the first layer's width or actual width upon that refractive index plus second layer's width upon the refractive index, like that, n terms, whatever are there. This is what the answer will be. Just not one term, but multiple terms will come. This d1 by mu1, this d2 by mu2, this d3 by mu3, like that. So as many layers are there. That is the answer. Okay. Yes, Arvinda, you can check not only this year's playlist, even the previous playlist. Even the year before that also. Nurture for 11th, Pathfinder for 12th. Or you can check Roar series, which are marathon lectures, or the current lectures will be beneficial because they are live. Okay, cool. Okay. Now, having said that, one last thing which I can tell you over here, especially this one. When there are these multiple layers, what happens is, imagine there is some object over here and you have an observer here. Because the observer sees through the slab, What happens is, this is the dense part, right? This is the dense part, right? So let's say this is air, this is having some refractive index mu, like that. And again, this is back to air. What happens is, when the observer sees that glass, this far end of the glass appears to be closer. So the far end of that glass appears over here. This is the actual side. This is the apparent side of that glass. So you will see that there is a shift. There is a shift which has happened, apparent shift which has happened of the far end of that glass towards you, towards you. So not just that, the entire world behind it shifts, and you will notice that the image will be formed over here. Image will be formed over here. So there will be an apparent shift which is present over here, and that apparent shift can be easily calculated. It will be this width minus this width. Now obviously this one will be your apparent depth. This one will be your apparent depth. This was your actual depth. This was your actual depth. This was your actual depth. This was your apparent depth. Always remember, from the surface you measured all the depths, correct? So that is the reason why apparent shift will be actual minus the apparent, but apparent is actual by mu. So T can be taken common. So T can be taken common into 1 minus 1 by mu. So this is very, very important formula. The apparent shift is T common 1 minus 1 by mu. T common 1 minus 1 by mu. Very, very important formula. Keep this in mind. The entire world behind that slab will shift by an amount of T into 1 minus 1 by mu. Very, very important. Let's see some questions coming up on your screen. First question, here it is. JK Tharan, can we skip any chapters in physics? JK Tharan, I have mentioned this again and again repeatedly. It's never about the chapters, it's about the subtopics. So please check this video. I've given the entire list of subtopics in the link of the description box of that video. There is a page of test series which will open up. You can download the subtopic list. In fact, it is also there in this video also, in that video also. Just go down to basically the Ekalavya Mains test series page. This is the test series which we are giving it to you full-fledged with 3 phases. Master plan is also there. Just go over here, download the subtopic weightage. Okay, download it. That will give you a good idea. Never skip chapters, skip subtopics. That is beneficial. Got it? So the handwritten notes will be uploaded on, first of all, like the video, guys. Yeah, it will be uploaded in the pinned message of the live chat, live comments, or even in the description box. Like for example, if you go to any particular video, let's say over here. So I'm just opening Namrata ma'am's video. So you can see session link is here. PDF will be here somewhere. Where is it? Ayo, PDF has not come up. Oh my god, flop show. Okay, maybe over here it should be there. How come it was not uploaded? Very surprising. Sorry, what is this? Why is the PDF not getting uploaded? Looks like I have to get in touch with the admin team over here. They have not uploaded. Last time, at least my lecture. Oh, my lecture PDF link is there. Why other lecture PDF links are not there? I'll just check with the team. But yeah, you can see it is there in the description box and also in the pinned comments. Okay, cool. It's right over here. Okay, so how do we do this question? First of all, a vessel of depth D is filled with some oil and the other half is filled with some other thing, the apparent depth when seen from the top. Basically, you have 2 layers. Each one of them is d by 2, d by 2. This is n1, this is n2. You are seeing it from the top, this particular object. So apparent depth will be first depth by refractive index plus second depth by refractive index. So d by 2 is common. So 1 by n1 plus 1 by n2. Take LCM. So it will be n1 plus n2 whole thing divided by n1 n2, and d by 2 will be over here. So that is it. That is the answer. One second, guys. Yeah, that is the answer. Option number 2, d by 2, n1 plus n2 by n1 n2. Okay, fairly simple. Let's do one more question coming up on your screen. Here it is. If a microscope is focused on an object, find by how much it should shift. It should shift if a slab whose refractive index is 1.5 and thickness of 12 centimeters is in between, is placed in between. Okay, that is the question. Let's try to solve, understand what it means. See, there is a microscope. Maybe this is a microscope and it is focused on some object over here. This is that object. This is that microscope. Now, what happens is you are placing a glass slab in between. The moment you place a glass slab in between, this object will form an image somewhere over here. That image will be the object because of that glass slab. So you have put a glass slab in between. So you will have to now shift that microscope somewhere here maybe. So you will have to shift that microscope like this behind so that you can see that object. Without that slab, you are able to see that through the microscope here. But the moment you put a slab, it will come closer. So whatever amount it shifts by, the same amount you have to shift the microscope. So that particular shift will be it will be T into 1 minus 1 by mu. Thickness is 12. 1 minus 1 by mu, which is 1.5. 1.5 means 3 by 2, isn't it? So 3 is here, 2 is on the top. So that will be 12. 1 minus 1 by 3 is how much? 1 minus 2 by 3 is how much? It is 1 by 3. So 12 by 3 is how much? 4 centimeters. So you have to shift the microscope by 4 centimeters so that you can see it properly. Okay. So this was your first scenario and this was your second scenario. I hope this is absolutely clear. So these are the kind of questions you can get on shifts or multi-layer liquid, okay, one after the other. These kind of questions, these are pretty much standard in your JEE examination. So all that we have done today is a single plane surface refraction. Next lecture we'll do curved surface refraction and lenses. Then we will go on to, combinations and all of that. And then finally prisms and dispersion. Cool. That's it from my side today. I hope you enjoyed the class, like the video and subscribe to the Vedantu JEE English channel. Bye bye. Take care.